Hi everyone, and my name is Ivan, and today we're going to solve path_sum LeetCode easy problem. Firstly, let's dive into task definition. We are having a binary tree problem. We are provided with root, and we have to enter an integer, targetSum. We have to find the path from the root to the leaf from adding these values, which provides us the targetSum at the end. So, in other words, look at this example. We have this direction from the root to the leaf. And if we are going to summarize all of these node values, 5 plus 4 plus 11 plus 2, we will end up with 22. And this 22 is our targetSum. But pay attention that we have to only use root to the leaf path. So if we are at the middle of these direction, find the 222, which is our targetSum, we don't have to return true. We have only return false. Yes, and a leaf, this is a node with no children. So 2 is our leaf. So let's start. Firstly, what I want to say before coding is just we're going to do it in two different ways. The first one is just we're going to implement this solution, provide the solution for when we are doing the summarization from 0 to targetSum. The other solution is going to be provided is just we are also moving from the root to the leaf, but we are not taking the 0 and summarize each of our node values. We are decreasing our targetSum. This is a very important thing because I want you to feel the difference between these two approaches, and these easy task on LeetCode allow you to do it. So let's start coding our approach. Firstly, what we have to define is the traversing algorithm. We have two traversing algorithms, BFS and DFS. BFS is when we are traversing level by level. DFS when we're doing the depth in first traversing, we're doing it in depth. And as you can see, obviously in our case from this example, even we can see that we're doing it in depth order. So BFS is not a choice for us. We don't do it in BFS way. So let's define our DFS function. Here we have to call our DFS and return the result from DFS of our as our final result. DFS is going to be called with our root, and because we are required for the first solution, we need the some variable, I don't know, sum, which is going to be populated, added from the current node to the next node, where this sum is going to be provided, conveyed properly. We need this sum value. How it looks like on practice is that, for example, we are on these 5 for root node. We are doing summarization with this node, the second node. 5 plus 4 provides us 9, and we're going to use this 9 to pass it to the next node. Not just start from the beginning or from these 4. We have to use this memory variable. In our case, this sum is our sum memory variable, which we're going to pass to the next recursion step. When we start doing it recursively, DFS is this recursive algorithm. When we're doing implementing recursion, we have to define firstly our base case and recursion step. Yes, and some logic is going to be, written at the middle. For the base case, what we have to do is just check when we have to exit our recursion, because recursion by itself is when we are calling the function again and again and again, and we have to define some step, base case, exit step, which is going to say, okay, algorithm, please stop doing it, stop diving further, stop implementing this recursion, and return this value to us. And recursion is implemented through not just when we are calling the function by itself. This is done like top to bottom approach, when we are calling it, calling. But when we define our base case, we are doing bottom to up, wrapping. We are just starting to move from the bottom to the up. And we also can, for example, define some logic on when we're doing recursion back. And we have to also remember it. So base case, in our case, if not root, we return false. It means what? If we got till the end, we are on this leaf node. We are, for example, on this 2 value right here. And we understand that, sorry, let's not use root, let's use node. Sorry for this. And when we are at this leaf node, we understand that there is no sum which provides us 22. We got till the end. That's it. There is nothing else to do. We haven't found our target sum, which is equals to 22. So what we have to do is just return false. This is what we have written here. For the recursion step, this is also a basic operation when we are just invoke our recursion for the left subtree and right subtree. Let's do it. We're just calling this, for example, for when we are on this 11 node, we are done it. We are invoking the left subtree, we are moving to the 7, and we're moving to the right to these 2 to find whether our sum equals 22. Our sum is equals to target sum. So it's done like node left, and we provide our sum here. The same is here, but with the right node. I mentioned that recursion is done not only when we're invoking these functions again and again, but backward step is also exist. And we have to define how we're going to pass this value from the bottom to the beginning, to our root. And we see that if we are, for example, return something from some value from the end, we have to properly pass this value to beginning. So what we're doing, we just define if some value, for example, has true, some of these values has true, we return true, return left or right. In our case, if for example, this 13 or 4 provides our true node, one of these nodes has true, we return true to this node. If, for example, we are on the one step further, closer to our root, if our 4 or 8 has true, we return true. Even though, even though this 8 is not our target sum, because we are passing this target sum from the root, from the leaf, we are passing this value. Okay. The main logic is happening here. We are starting from our 0, of course. And we have to define our main logic at the middle of this recursion. And we define if our sum equals target sum, we return true. Looks great. But we have to also the property of root to leaf condition. And it means that if our sum, for example, in this case, if we have sum, we can find some sum which is equals 22, and it can be in the middle of our direction, in our path, direction path. We return true because it's 22, it's equals target sum. We return true, and that's it. We are done. But we are mistakenly provide the result because we have to define only the path, route to leaf path. We have to define whether at the end of this path we have target sum. Only at this moment we have to check whether our sum is equals to target sum and return true, not at the middle. This is just by condition of this task. So what we have to do is just add additional condition. If not node left and not node right, we check if our sum is equals to target sum. That's it. That's it. If not, yeah, sure. And currently we are add this logic, and we even only when we are at the leaf node, we check if our sum equals to target sum, and in this case return true. Otherwise we are return false because this is our base case. And this is the great example. Let's check whether it works or not. Yeah, it doesn't work, and let's check why. Firstly, what it can be. It's not a mistake, but we are providing the false. It has to be true. Root is provided, sum of 0. We are starting from root and sum of 0. It's right. If not, return false. The base case is perfect. If no, the root to leaf condition when we are checking. Sorry, of course. We have forgot just the main thing. We have forgot to summarize our not value. How are we going to do it without providing the summarization to our sum variable? And that's it. I think it has to work perfectly. It has to work perfectly. All conditions are incorporated. All corner cases are defined. So we are good. Let's move further to the next solution. This one I will write like V1. Let's start from the V2. I'll copy some cases. So I'll make it open for this. For the solution 2, when we're not just summarizing it from the 0 to our target sum, but we're decreasing our target sum, we again have to use DFS algorithm. But pay attention that for this case, for the first solution, we are required additional sum variable which we're going to pass to the next node, from the current node to the next node from the recursion step. When we are just decreasing target sum, we are not required. We don't need additional variable. So we can use this one. We can use this target sum by itself, and we don't need to create and at this case we don't need to create this separate inner DFS function inside. We can use just this has passed sum function, which is going to be our DFS function. This is just awesome. We are safe. We are safe time. We are safe. How to say it? We are safe lines of code. It's more readable. And faster to implement. So we have the same base case. Anyway, we have to use it. This is our DFS function. It's just called differently, but this is DFS function. What we're doing, we just check for the root, because we're going to use root in our case. Just imagine that this our DFS function. It's here. for this case, we are taking our target sum, and we're decreasing our node value. We are also use completely the same structure for checking root to leaf condition. If our target sum equals 0, only in this case we return true. We implement the same recursion step, completely the same. But what we are doing, we just add our, invoke our root left and root right. And last but not least, we have to return our left or right. And that's it. Let's check that no mistakes exist. Root. If not root, we return false. Target sum decreasing the node value. This is the same condition. If target equals 0, we return true. Left invokes properly, subtree. Right subtree invokes properly. We don't need this mistake. We don't need this sum value. But we need to provide, instead of sum value, we need to provide the target sum, updated target sum. And we just return it. Node is not defined. Node is not defined, right? Because it's not node, it's root, right, in our case. DFS is not defined because we're invoking our has passed sum. This is a problem when you are doing copy. And again, of course, we're in class solution, so we have to invoke self has passed sum and not has passed sum. And that's it. Don't worry about mistakes. It's completely fine. You're learning when you are making mistakes. And you can see how I find the solution and use these patterns also. So it's accepted. Let's submit our case. It's going to be submitted. This one has passed sum, and it works. It works. It's what we needed, and in reality, this is very great. This is a very great task because it provides you idea of how to apply DFS algorithm to our binary tree. And you have to understand that if you see that you may find the solution without defining our DFS function inside, in other words, you understand that you may use this, this argument value as it is and not create something else. This is the most efficient and properly the best way which you can provide it to your interviewer. So I wish you did it this way. Okay. Probably I think I told everything. In terms of time and space complexity, everything I believe is obvious. These two solutions are completely the same. The difference is just in defining of this DFS function. In terms of time complexity, it's log n solution because we are in worst case. Yes, not in worst case, in average case, it's log n solution because we have left and right subtree, and we always divide it by 2 when we are moving to our leaf. So in average, we are providing only, we're doing it for all log n time complexity, where n is number of our nodes. In worst complexity, this is OM because our tree can be not like this. It can be not balanced because you can see that it's balanced in some case, but it can be just a line where we have only, where all the nodes has, for example, only left subtree and not right subtree. And in this case, our time complexity is going to be ON. And this is the worst case. But in average case, log n. I think that's it for today. You probably got really really good example, and I believe it was helpful. So what I wish you is just keep moving, have a happy coding day, and see you on the next video. Bye.